Good evening. I've moved my camera back to my old position. I think I like that better just for the way I feel. It might look wrong, but I guess it's the way it works out. So hopefully everyone's having a good week. I started grading 5. It's assignment 5. I know it's horribly behind schedule, but I intend to get that done shortly. And then get 6 done as quick as I can too. I'd like to have that done by Friday. We'll see. I'm determined to work on it, so we'll get it. So yeah, and we have an exam coming up next week, right through chapters 4 through 6. So our second exam. That's why I want to get those graded, so that way you guys have that feedback. All right, so which means actually what we're talking about tonight doesn't even part of it. So the next thing I want to talk about is there's two main topics for tonight. The first main topic is magnetic tapes. And you might think, well, that seems strange because we don't use them. And as regular customers, you're right, we don't, but they do get used. And I'll explain some of that as I go through it and why they're used and how they're used. Some of it is legacy. It's kind of the old way of doing things. But we do have to learn a little bit about that because that history is important. Not because the history is there, but then you can kind of understand where things are in the world. And by the way, magnetic tapes are still in use today, every day, they're used all of the time, especially on mainframes. So we'll talk about it as we get there, when I get to the spot where I want to talk about it. So I think early on, actually, let me see if I can open up here an image for you guys. Let me do this off screen here. Reel-to-reel machines. Oh, jeez. So let's see if I can't find one here. Oh, here's a good one. So this is, I think this is for sound, but it's similar, right? This magnetic tape. And if you, until very recently, they continued to even do movies with the reel-to-reel. I think they've gone completely digital now. Let me go back here and see if I can't find a better computer. Yeah, okay. So if you've ever seen pictures like this before, I should have made this my thumbnail. That would have been cooler. I don't spend a lot of time on the thumbnails because I figure no one else is really coming here except for people who are in the class, so it's not that big of a deal. So there's a very interesting movie. And I watched it and I liked it. I don't like everything about it because it's not perfectly historical, because I'm a guy who likes history, but it's pretty close, and I'll give it its due. And the movie is called Hidden Figures, and it focuses around 3 African American women who are working for NASA, and actually, interestingly enough, they're working as computers. That's their job, is they compute. And it's an interesting movie, and I suggest watching it. And then after you watch it, I would suggest going and looking up the historicity of it, because there's a few things that they don't quite do right. The guy who plays Sheldon Cooper also is in that movie, so it's kind of interesting watching that actor in a different role. Although he's still a big nerd, so I don't know, but it's fair enough, right? He's good at that role. Okay, so in that movie, it does talk about these computers here, and because while these women are at NASA, they switched over to computers, to not human computers but digital computers, and this is examples of that. So they didn't have the disk drives that we have now. They had these magnetic tapes, magnetic tapes. And so I didn't even know frame of reference. The technology is very similar to a VHS, although my guess is most of you probably don't use them very often. If you probably know about them, but you probably don't know how they or aren't super familiar with them. But a VHS, the 8 tracks, which even my generation barely knows about those. That was what they had before cassette tapes, which is also the same kind of technology, and then also later on, you've got CD-ROMs and things like that for your music. But all of those technologies, anytime you have a magnetic tape that's very thin and very flimsy that spins and has information on it, and it moves. So these tend to move much faster than any of the other technologies, just because a computer can read very, very quickly on it. And whereas if you're going to do something with audio, you have to slow it down so that you could pick up the information on it, so that because all of those, that they're not necessarily backed by computers, in that they're reading the data and immediately pushing it out to the speakers. So it's a little bit different in that way. And so they have to slow it down, otherwise the music would sound really weird. I suppose they could compensate for that, but whatever, doesn't matter. So I'm going to talk about 3 different ways. 2 different ways that we can store on these tapes. Now, so how about this? Just magnetic tape for a computer. No. Oh, geez. It doesn't know. So this is what they look like more so now today. Oh, you know what I should do is just go to Newegg. Man, there. It's not necessarily the best site, but it has a ton of stuff on it as far as computers, especially when you're building your own. What do I want to do? Magnetic tape. I spelled it wrong. Yeah, I meant magnetic tape like this. Trying to see if we can... No, okay, I'm putting the wrong words in here. Maybe we'll get one here. Yeah, see, these are all hard drives. Tape drive. Okay, so these are tape... Yep. I think there's slots in these. Yep, tape drives. Now what? Yeah. All right. So, well, I found the drives, but I didn't find the tapes themselves. I'm sure it's just a matter of finding the right word. Mm-hmm. What do we call it? Tape storage? And then I spelled storage wrong. Man, my spelling is just really... As soon as I get on cam, my spelling gets really bad. Yeah, okay. Well, none of these are actually examples of the tapes themselves. I've used them. I had a job where I maintained a fairly small server. Oh, here's a tape. So let's see. Oh, that doesn't even show us anything for it. Okay, well, that's a bummer. How big is it? This is 6.25 terabytes. Oh, compressed. 2.5 terabytes uncompressed. That's pretty good, isn't it? Yeah, that's more than my hard drive. That's more than my hard drives on all of my computers probably put together. Maybe not. I'd have to go and look. I'm not going to spend that time. Okay, let's close that. So they're still used today, but we'll talk about the old kind of the old way first, and then I'll talk about it. Three different. I think it's three different ways. Is it three? No, just two. Sorry. Okay, so this is how the tapes work. They're big, long strings, and they have tracks on them. And so these tracks here, it'll read a number, and then it'll read another number, and then another number, and so it just reads one bit at a time. And they're lined up like this. My hand is pretty steady today. Of course, I say something and now it gets all wiggly. Yeah, it started out good. All right, so they'll come like this, and there's different ways to kind of read this. Let me go through this, and I'll kind of show you guys, because it's actually pretty neat. First off, what I want to do is I want to grab this, copy it, go down here, and paste it in, so that I have a second copy, because I'm going to do it different on the second thing. Okay, so the first one is called Serpentine. Yes, that means like a snake. Okay, so what happens is it's going to go like this. 1, 2, 3, 4, 5, and it reads all the way down to the end here. Say, right, what doesn't really matter, it's, say, it could be 1,000 or whatever. I'm just going to call this 100. And then it goes down to 101. And then it starts working its way back. And then it'll go all the way down to the other end, to say 200. And then 201. And then it starts going across here. And it reels back and forth. So what happens is the tape is connected on both ends, and so the tape will run down until it gets to the end, and then when it gets to the end, then it's going to run right back around the other direction. So it's going to go back and forth. Not super efficient, but because it's only reading one at a time, it's only having to read one bit at a time, it can go very fast. And comparatively, right, it's still really slow if you compare it to, say, RAM, but it's very fast compared to, right, if you wanted to read all of them at the same time, it creates a little bit more complications, potentially. Okay, so that's the Serpentine, and it's done linear, right? That's what they call that. So this is just an example of how to do it. Now, the difference is in the early days, and this is still true today for some things, is all the different companies that made tapes, they'd have their own tape drive, and then they would manufacture the tapes. So you had to buy the tapes from them, but because they had different formats for how they did it. So this is one way to do it, but they had different ones had different ways to do it. So instead of coming up with a standard, which they didn't do that. They all came up with their own standard, each company. Trying to think if there's something we saw that with. We used to see that, well, the closest thing I can think of, at least currently, although it's not a disposable item, is power cords for your laptops. Right? If I have a power cord for my laptop, that necessarily won't work on yours, unless it's the same make and model. Maybe in the Apple world. I'm not well enough versed about that, so it might not hold up in the Apple world. So what this does is it compacts the data. So all the data is right there, right? It's going to compact it. It puts it all together. But if it needs to look for, say, the 500th thing, it has to run back and forth 5 times before it can. In this case, right, because I had 500, right? But if I'm looking for something that's very far down on the list, then it might take a while. Now, there are ways we could do, things we could add to our algorithm to make it jump, and that would help. But it's still slow, comparatively. Not slow, it's just, it can spin quickly, but it can't it can't search very fast. So and it can write quickly, but again, it takes a while to search for things. So a bunch of companies, 3 companies got together in the late 90s. In 1997, so Hewlett-Packard, IBM, and Seagate, and they were 3 of the big producers of these tapes and tape drives, and they came up with a protocol where they would all be the same, so your stuff would be interchangeable. And so what that does is, it's a little different, and instead of going linearly, it stores a number like this. It's not the right way to think about it, but it stores it at an angle. And the reason it does this is because it can have multiple heads on there then. It has this wheel in there that spins against the tape. As the tape goes, it spins against the tape. But it moves as it goes. And so it's able to read these as it goes down like this. And you say, well, why is this good? Well, because if the tape fails, it's going to fail in bursts, just like we talked about before. And now it's easier to rebuild when we have a problem. So this is so the most latest. Oh, actually, I should probably bring that back up again here. And do I have restore closed window? Yeah. Let me just try this. No. Oh yeah, they're right here. Okay. Except for I want to look at the actual product. This is probably the best picture I've seen so far. Yeah, these are transparent. You can see through them. And it's got this head that reads the tape as it goes by. So, but we don't want that. We want... Here's a cassette tape. So that's actually the interesting thing. Some computers, probably a little bit before I graduated from high school, so back in the 80s, they didn't have hard drives. They didn't come with a hard drive. And so if you wanted to boot it up, you had to put in the disk to boot it up. But before they had disks, they had cassette tapes. So your operating system would actually be on a cassette tape. So you just put that in your computer drive, and then it would run. Really neat. Now, actually, I got an interesting story about that, and I'll tell you that in a minute. So one of the things that... What was I looking for? Oh, I was going to look to see if I could find specs on these. Go here. The advantages, disadvantages now. Okay, well, let's not worry about it then. Because the book tells us that the newest generation is I don't want that either, is Generation 5. Gen 5. And that could be about 1.4 terabytes. But the one we looked at was, what, 25? No. Yeah. Or 2.5, and then 6 something for compressed. This is uncompressed, and then this one it doubles, so 2.8. So compression algorithms take take numbers and kind of mash them together without losing the data. So you can rebuild the full-size number. It's pretty interesting how it works. There's a bunch of different kinds of compression methods. I think this came out in 2010, so it's probably due for a Gen 6. But one of the things that's useful, this is called LTO, or linear tape open, which means that everyone knew what the standard was, so it wasn't proprietary or hidden. So one of the things that's very nice about these is it's called deep error correction. Now, we talked about error correction a little bit. So, error correction, I think we talked about Hamming codes, right? So, error correction means that if we lose a couple bits, one or two maybe, bits, we can reconstruct it. Well, no matter what we did in Serpentine, if we lost a string of, say, 8 of them together, there's nothing we could do. We would just be out. We just lost that data. So, but in this strip, sometimes it'll go out this way and sometimes they'll go out this way. But they don't go out diagonally. So it builds it diagonally. And I'm showing you a much smaller one here, right? So typically you're going to have 8 or 15 or 18 tracks. It's going to be pretty big number of tracks that are run. But these are at a diagonal because if that burst happens and a bunch of things get erased, it can still rebuild it. Now, it probably can't rebuild it in that part of the tape because that part of the tape is spoiled, but it can move it someplace else and now put it there. So that's important to note, is by doing it at an angle. And now it seems kind of silly, right? That just like, well, at an angle, that's enough to make it better. Yes, it is. So, and people spent lots of time and money figuring out how to do it that way. So, okay. So deep error correction means that you can correct burst errors and single errors. So burst and single. So both of those errors can be corrected automatically. We don't need human intervention at all. It can just rebuild it. The other thing that's actually neat, so these tapes are used primarily for backing up mainframes. So if you have a lot of data on your mainframe and you want to make sure that you never lose it so that you can restore it later, a lot of times you'll use these tapes. But the problem is it stores the tape. It might store the state of the server currently and store it onto this tape. But you have to come in and change those tapes periodically because, right, they fill up, and that's a problem. And their tapes aren't super cheap, but they're well, I'm sure within. Oh, this is the cheapest way to actually store data is on these magnetic tapes. So the problem is you have to send a person around to change them. Well, right. Well, the person's probably got to have a little bit of technical knowledge, not a lot, but a little bit. So it's not just everybody, which means it costs more for that person. And then the other thing is it's really a repetitive and boring job. So you probably are going to turn over people pretty fast because people don't want to do it. So what they did is they came up with these robotic tape libraries so that you can actually put a robot that will change the tapes for you. It's pretty cool. And then it creates a longer period that you're going to have to go back and look at it. I would be surprised. Well, it's possible that things like Google or Amazon do not do tape backups, but it's also possible that they do. So I have a friend of mine who works at a bank here locally. He's the chief security officer. And they back up their system. And like once an hour, something like that. Maybe it's even more often than that. So, and that's everything on their system, not just the financial records. So it's very difficult for them to lose data. They also employ something we're going to talk about in a bit, and that's called RAID, so that it's super unlikely that they'll lose any data. And then everything is extra redundant. Like, it's not just in double or triple, it's in like quadruple, because they don't not want. And one of the things is off-site. So if there's a fire in the bank and the whole place burns down, they won't lose any of their records because it'll be on a different computer at a different site. It would have to be pretty catastrophic to lose that information. All right, so, which is a good thing. All right. Oh, interesting story. In fact, it was from the same friend of mine. Remember what I said? I said that the old computers, they used these tapes. That was their hard drives. It was a cassette tape. It looked exactly like a cassette tape. In fact, it was a cassette tape in some cases. So he had, he was in high school. So and it was before I knew him. But he had written a computer program to do, some intricate thing. I don't remember what it was. But it was, he had spent hours and hours and hours working on this. And his dad, who didn't understand technology at all, finds this cassette tape, and so he pops it in the cassette player to see what music is on there, and all he hears is, and so he's like, well, this is nothing, and so he records over it. He records some songs off the radio or something. So my friend lost all of his work, hours and hours, maybe 100 hours worth of work, working on this program because his dad tried to listen to the music. So it's actually kind of funny. Although I'm sure he was not happy about it at the time. It does make a pretty good story. Okay. Okay. Let me just split this here. Today might be a little short. We'll see. We'll see how it goes. Okay. So in 1988, David Patterson, Garth Gibson, Randy Katz from the University of California in Berkeley. They wrote a paper, A Case for Redundant Arrays of Inexpensive Disks. Redundant arrays of inexpensive disks. Otherwise known as RAID. Not the stuff you kill the wasps, although that's a different kind of RAID. It's not what we're talking about. So it's a RAID disk or RAID data. So what they did was they said, well, there's some problems with having just a single hard drive. Because what happens if that hard drive fails? If that hard drive fails, you've lost all the data on it. If you've ever had that happen, it will cause you generally to be very upset about it. You don't like that. So one of the things is here, they've actually did this. And they changed it to independent. Independent. Redundant arrays of independent disks. Semantics. But it means that we can actually use expensive software. We can use hardware. So we can use expensive drives if we want to. Perfectly fine. Okay, so I'm going to talk about 6 or 8, more than 6, about 8 to 10 different ways to store data on multiple disks. At least 2 of them are theoretical. They don't really exist in the world because they're not good, but they're in place because they're the natural progression from the one before. All right, so what I'm going to do is I'm going to start out the first one. So it's computer science, so we're counting, right? So where do we start counting? 0. RAID 0. Okay, so RAID 0 uses a technique called data stripping. Or, and this means the same thing, drive spanning. So what it does is it takes the data and it splits it up. It splits it up into strips. Strips, I think this exact same thing as we thought about for blocks, except for they don't have to always be the same size. We're going to break it up into some pieces. It doesn't really matter. They're just pieces. And then we're going to put the first strip on the first drive, the 0th drive, and then the second strip on the drive 1, and then drive 2, and then drive 3, and then drive 4, until we get to the end. And then we'll come back again to the 0th one, and we'll start there again, and we'll just continue growing. And so that's how we'll save our data. And there'll be a controller somewheres that can figure out where, when you're looking for that memory location, it knows how to decode and figure out which drive it's on, so it can send you to the right place. Does that make sense? Right? So, so we say this is D1, D2, D3, D4, and so we're going to go 0, 1, 2, 3, 4, 5, 6, 7. So, and it'll continue doing that the whole way. That's a good way to do it. The problem is there's no redundancy. So if one of these drives fails, we just lose a certain percentage of our information. This is also why it's called RAID 0. It's really not RAID. It's just a bunch of disks that are helping us, but it's not, because one of the advantages of RAIDs, and we'll see that as we go, is there's redundancy built in so that if a single drive fails, we'll be able to rebuild that drive pretty quickly after the failure once we get a new drive in. And it can do it automatically. It's pretty neat when it happens. Okay, the next one is RAID 1. So this one, you can think of this as 1 as being 1-to-1. So what we do, this is called disk mirroring. This requires pairs. So we'd have disk 1, oops, disk 2, disk 3, and disk 4. So anytime we write something, we're going to go 0, 0. Oh, no, I'm sorry. Because this doesn't... Okay. Oh, yeah, it does strips. So, yeah, those are the numbers on the strips. So this is... So, 0, 1, 2, 5, 9. Then it mirrors it. 0, 1, 2, 5, 9. And then what? 3, 4, 6, 7, 8. 3, 4, 6, 7, 8. Right? They're just simply mirrored. Now, the advantage to this is if any single drive fails, we can pull that drive out, we can put a new drive in, and we just simply copy everything from its pair over to the new one. Pretty simple. This is great. But it's expensive. Because if each of these drives is, say, a terabyte, right, it takes 2 drives to save 1 terabyte. So we have to double the amount of drives in order to save it, so we have that redundancy. Well, that's great. Oh, actually, I wanted to go up here and talk about what does redundancy mean. Redundancy means... It means like repeating. So, but in this case, it means something just a... Well, doesn't... Actually, that's still its meaning. It also can mean not useful. Okay, well, all right, let me stop. Redundant, definition. Not or no longer needed or useful. Okay, so that just made it even harder. Okay, never mind. Many of the old skills have become redundant. Inessential. That's a really great way to say it. Or unessential. Needless. Unneeded. They're all synonyms. I mean basically that version of the meaning. That's not the version of redundant we're talking about. British. No longer employed because there is no more work available. Able to be omitted without loss of meaning or function. This is the meaning we're talking about. Or this one, not strictly necessary to function, but included in case of failure in another component. This is a great, this is good. Yeah, in engineering, perfect. So what it means is we're going to add some extra drives, and we're coming up with ways to make it so that if one of the drives fails, we can rebuild. And we're just going to look at some different ways to do it. Okay, so RAID 0, not technically redundant. Because all it does is it spreads it out over all these different drives. So that's not necessarily RAID, but we call it RAID 0 just kind of as a baseline. Although we can use it, and I'll show you how that works before we're done. Okay, redundant. An array, of course, is like a list or a group. In this case, we just talk about a group. And then inexpensive or independent, and then disks. We all know what that means. Okay, good. Just sometimes it's helpful to break those down and not just take it as a whole. So to kind of see how they got there and why. Okay, so why is this not going down? Did I get to the bottom of my space here? No, I did not. But now it's working. Now the thing's working. Okay, well, whatever. All right. So, expensive. Bad. Oh, now RAID 2. And this is the first one that's theoretical. So what we do here is Each drive gets 1 bit. With Hamming drives. Remember earlier in the semester we did something with Hamming codes, right? Where we added in Hamming bits or parity bits. Well, they're not parity bits per se, but they're Hamming bits that are in place so that we can rebuild if there's a failure. In fact, actually the cool thing about Hamming code is we can rebuild if there's multiple failures. So what we do is we take a single word and we're going to put it all in the exact same place on the drive. And so we take this big word or big whatever it is, right? Because it depends on how many drives we have, because we could have dozens. And we take 1 bit from each of it and we put it into position. But then we actually have some extra spaces in there because those are Hamming drives. And it allows us to rebuild if there's ever a failure of any one of the drives or potentially multiple drives. There is a maximum limit that could fail at the same time. So you'd think, well, geez, hard drives don't fail at the same time. Well, yeah, except for if there's a lightning strike or, you know, a massive electrical surge, you can get them all to fail. And one of the things is industry uses these, right, on servers. And what happens is they buy all of them at the same time. Well, just like light bulbs, they don't all go out at the same time, but usually, well, nowadays we get the LED light bulbs. I guess that's not a very good analogy. But a lot of times when they start going out, if you've replaced them all at the same time, or batteries or whatever, right? If one goes out, you might as well just replace them all, right? Because all the rest of them are likely to start failing soon. And indeed, that's actually what happens a lot of times in industry, although sometimes there are shortcuts taken. And the different RAID strategies will actually help you with that because they can survive multiple drives failing. This one can, right? The problem with this one is to do 1 byte, it takes 11 drives. If you're going to do an 8-bit byte, because you have to have 3 Hamming bits, and that's 1, 2, and 4 in order to get there. Actually, no, it's 1, 2, 4, 8, so it's 12 drives. So, because that's what it requires for Hamming. So, that's the problem with this one. This is theoretical. RAID 3. I know, big surprise, right? Okay, so RAID 3 says, well, Hamming codes, they're great, but there's too much of them. So this one says 1 bit per drive. With a parity drive. I was reading some stuff on this earlier, and actually it turns out that usually they're almost always odd parity, so that at least 1 bit in one of the drives will be on, will be a 1, and that's required in odd parity. So the cool thing is, right, you can take all of your bits, 0, 1, 1, 0, 0, 1, right? Because that's what this is all doing, right? And the cool part is, You just do an exclusive OR between each of them. And now it's going to be hard to read, but so in this case, we say exclusive OR. Okay, that's a 1. Now we exclusive OR that result with the next one. Oh, that's a 0. That's a 0. That's a 0. Then we get to a 1, and then a 0, and then a 0, and then a 1. So this means our parity is, well, if we want to do odd parity, means we need it to be a 1 at the end, we would do 0. And if we count 1, 2, 3, 4, 5, haha, there's an odd number of 1s, so our parity bit is a 0. So, and the computer can do that, the XOR pretty quick, so which is awesome. Okay, so that's RAID 3, and that's real. They do use it. So then the next one is RAID 4. Again, man, their naming is so awesome with this. Just goes right in sequence. This one is also theoretical. So this one says, so instead of taking 1 bit per drive, it's a strip per drive. In this case, we want them all to be the same. And then you have a parity drive as well. So what you'll do with this is you'll look at the first position. So let's say we had these numbers 1, 1, 1, 1, and 1, 0, 1, 0, and 0, 0, 1, 1. Okay. So those let's just say we have 3 for simplicity. And we wanted odd parity. So we would look here and we'd say, oh, there's just 2 there. And this is just an XOR, but you do it in place. So there's never any carries. So this, we're just looking for exclusive OR, and we want it to be a 1. So, oops. What we're going to do is I'm going to draw a box around this. Again, this is odd parity. So we don't know what these are going to be. So let's start over here, and there's just 1 of them. So that is an odd parity, so we're going to go ahead and do a 0 there. This is also odd parity. We do a 0 here. This is odd parity as well, right? There's an odd number of them. This one is even, so we're just going to go ahead and do that. So that gives us our new strip, and that's how we do that. So the problem with this one that actually doesn't happen on the others is that if we have a lot of data, we have to redo that parity strip every single time. In RAID 3, we're just going to push it out there and we have that 1 parity, and we can kind of calculate that in real time as we go. In the RAID one, it takes longer to do. And so if we're going to write a bunch of different things, they're going to get backed up on us as we're computing that parity bit, so we can write that out to our parity drive. So then we have RAID 5. And by the way, this one is actually quite popular. Or it used to be quite popular. So this is the same as 4. Except the parity, I'm going to call it the parity strip. rotates where it's going to be. Instead of saying where, let me back this up. Rotates the disk it's on. So, you say you had 7 disks, and so it would be on the 7th disk to start with, and then the next time you wrote more strips, it would be on the 6th disk, and then the 5th disk, and then the 4th disk. And this is where it actually is faster. So you'd say, well, that doesn't speed anything up. But it does, because we write on the first 6 drives, and then we have to calculate our parity strip. So it calculates that parity strip, but while it's calculating the parity strip and getting ready to write that onto the 7th one, then the next set of strips can come in, and we can write those on the next level. Well, the first one is computing, and so then it can write onto the 7th one. But we skip the 6th one this time. So it was 1 through, or the first one, 1 through 5, and then 7, and so then we'll skip over 6, and then the next time we'll skip over 5. And so what happens is we can back up these calculate things, and we can write them later, and so that we can move on and keep moving. So it's kind of like a pipelining idea. Now this is really great, and RAID 5 is amazing. It can replace any single drive failing, and it can do it fairly quickly. The problem is again, sometimes it takes a long time to repair it. There's actually one the book doesn't talk about. It's a version of 5. And what it does is it calculates the missing data, and then it rebalances everything. So when a drive gets destroyed, it says, "Oh, we used to have a set of 7, but now we only have a set of 6." And so it reassigns where the parity bits are and recomputes everything. And it just worked really hard to do that. But it resets up so that there's these parity bits across the board. Again, but it assumes its system now only has 6 drives. So it's not waiting for that 7th one to show back up again. That's certainly one way to do it. It causes a lot of work, computer side, which is power intensive, and if there's a second drive that fails, well, it's rebuilding. Of course, that destroys that. Although that's a potential danger in all of our systems. But what happens is anyways, on a normal RAID 5, it won't do that. But what will happen here is that sometimes it takes a long time to replace that. Well, think about it, right? Let's say somebody at my bank, because I happen to know how it works there, right? One of their hard drives fails on their RAID service, so somebody now has to, and maybe it's at 3 o'clock in the morning, right? So the alarm goes off on my friend's phone, and he has to get in his vehicle, and he has to drive to the bank, and he has to go in, and he has to replace the drive, and they have enough new ones there to be able to deal with it. But what happens if they don't have that policy, right? A bank is really concerned about their data. But let's say you work for a company that just says, you know what, nobody comes in on the weekend. Say it fails at 6 o'clock on Friday night and everyone's already gone home. Well, now it won't be fixed until Monday morning, which is fine, unless another disk fails. Or again, like I said, if you have lightning strike or something like that, that creates catastrophic problems. So this is where 5 fails, is the fact that if more than one drive fails, it's just done. There's nothing it can do. Bring in RAID 6. It's important to note that actually they've done studies on this, on how often or how do the discs fail. And a lot of times what will happen is once one disc fails, then another one is very likely to fail soon. Maybe they just have sympathy for each other. They all go at the same time. Or they just all have the same tolerances and they wear out similar times. Alright, so what this does is this adds a second error correction strip. Except in this case it uses Reed-Solomon. So we're not going to talk about how this works, the Reed-Solomon. But what happens is it has one parity strip on one of the drives, and then it has an additional independent error correction strip that uses Reed-Solomon. And so it's not a parity bit, and so it's a different system. And we won't talk about how that works. I'll leave it to you guys to look that up if you want to. But now there's two different error correction things, and one can correct all of them and the other one can correct all of them. So we can rebuild even if two discs fail now, which is really great. So that's the reason why this is in place. Okay, so then the next one, and this one is fairly new actually. The last time I taught this class, I didn't get a chance to cover this. DP. Double parity. So this is in some ways like 6. Okay, so, right, double parity. So you'd say, well, doesn't that sound like RAID 6 to you? Well, maybe a little bit, except for there's a little difference here. I'll show you. So let's letter our drives A, B, C, and D. And then P for parity. And Q for our second parity. We could say P1, P2, but I'll call them P1, P2, but we're not going to do that. Okay, so 1, 2, 3, 4. Okay, so this is where this gets kind of interesting. Okay, so this one here, I'm going to say this is, well, let's not do that. This will be A1 exclusive OR B1 exclusive OR, oops, C, C1 exclusive OR, D1. So it looks across here, which is what we saw before, right? And if we wanted odd parity, we would then have to do an exclusive OR with a 1 at the end just to make it work. And these are strips, by the way. So these are strips, again, not bits. Okay, so now here's the interesting, this is where it gets a little interesting. This is A1 exclusive OR B2 exclusive OR C3 exclusive OR D4. And then here we would see A2, and I'll just put the dots here, because it'll be A2, B2, C2, D2. This one, however, it starts at the same place, and then it goes to B3. Oh, wait, I'm sorry. Yeah. C4. And then P1, not D. So it'll go across down like this and then come up here. Or not come up there, come up here, up to P1. And then the same thing here, we'll go A2, B2, or A3, B3, C3, D3, and then A3, B4, P, no, actually, I think I'm messing this up. Yeah, I am. I switched my directions from my notes. That makes it hard. Okay, so this will be B2, C3, D4, P1. So it goes down like this, starting from 2 here. No. I got the numbers wrong. Yeah, I'm getting the numbers wrong. B1, C2, D3, P4. So it goes diagonally down like this. When it gets to the end, then it goes up to the top. And then it'll do the same thing here, A, but then it switches over to C here, and it does another diagonal run. So you get the idea here. What it's doing is it's creating these diagonals. Now, those diagonals, what they do, what that means is that this bit, well, let me back that one up and let's look at a different one. Let's look at A1 here. A1 is stored right there, but it's also stored here. So if A fails, we can use either P or Q to rebuild it. We can run either one and we'll be able to figure it out. And maybe the easiest is P because it just goes straight across. Okay. Now, but what happens if both of these fail? We can't use this one anymore, right? Because exclusive OR, when we do the exclusive OR and put them all together that way, as soon as we have 2 errors, we're out. There's nothing we can do. We can't assume anything because all we have is odd parity and even parity, and we don't know. We don't have a clue. If one of them has to be a 1 and the other one doesn't, we don't know which one is supposed to be a 1. But here's the part that's cool is we go over here And look, oh, look, lo and behold, this is on a different one. So we can use this formula to rebuild that spot, and we can use this formula, or that, I'm sorry, this top formula to get this one, and this one to get that one. And so, and we can rebuild all of them that way, because we can combine the two. So we can say, well, which one is supposed to go where? Well, we go down and look at the next one. And that will help us rebuild them as we go, and it actually allows us to rebuild if two failures at the same time. Okay. So the very last thing here, and then we'll be done, is hybrid. And so we can combine any two in a hybrid system. Actually, we could do more than two, but here's two of the more popular ones. That's 1, 0. So this is a collection of RAID 1 of RAID 1s connected with RAID 0. Let's see. Let's go here. Oh, this names it back. It names it different. Well, yeah, there it is. Okay. So this is a great picture. Actually, Wikipedia is helpful. Aha, yay. All right. So what happens here is this is RAID 1. This is a RAID 1 system. Remember, RAID 1 is redundancy, so everything's the same. But then we say RAID 0. So when it gets in here, it's going to assign the first bit here to be doubled, and the second bit here to be doubled, and then doubled, and then doubled. Or are we in strips there? Sorry, it's strips. So the first strip goes here in both places, the second strip goes here in both places, and then back and forth. So it helps us load balance as well as we go. So the next one, or another one, oh man, there's a ton more here, is RAID 5, 0. And that is, each of these is 5, right? So 5 says, oh, right. 1, the first strip, the second strip, a parity strip between the two of those, and then it has B. It's kind of hard to see in there. Maybe I can make that bigger. Oh, we can. Okay. So then B here, because it splits it up, and then C, and then puts the parity. So it rotates where the parity bit is. This is a great visual. But the first strip goes in here, the second strip goes in here, the third strip goes in here. So that it helps, again, spread it out. So that, right, if there's problems, those problems they won't be super localized. That's the idea. Let's look at some of these other ones. All right, so this is RAID. Okay, so this is just redundant, 2 redundant RAID 0s. That's useful, but it's 4 drives. Well, fair enough. Here we have some RAID 0s, just switching back with our strips, right? A strip here, a strip there, a strip there, a strip there. Well, oh, this has 3 layers. Oh, no, only 2. So this is a RAID 3. And a RAID 3 means this last one is a parity bit. So the parity strips. So the parity for this one is over here, and then the parity for this one's over here, and it just goes down like that. And that's actually pretty interesting. Each of these has a different way of doing it. We talked about the 1, 0, and then we have a 6. 0. So each of these is 6s with both 2 different parity bits. They're usually used different ways to achieve those parity, though. Yeah. And then, right, then we go, the same thing over here, right? So, and this is just the parity for these two. Now, usually they're not going to be 2. There's going to be more like 6 or 8. So it's a little bit bigger. And then we could do this one. Oh, yeah, that's a multi-layer, right? So it comes in here to a RAID 0, and that splits between 2 RAID 1s. Blah, 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 blah. You can kind of see how these all work. So the first one goes here, the second one, the third one, the fourth one. Although I don't know why you would include the extra layers. Yeah, I can't think of the reason why you would do that, because they're all the same protocol. It's just going to put one here, then there, and then there. Yeah, so you might as well just put them all with the 0, 0, 1. Right? Like this. Except, or no, the other way around. Sorry, it'd be a 1, 0. It'd be the same thing as a 1, 0. The only thing is instead of having only 2 1s, you have 4. Yeah. I don't know why they did that. It's a strip of RAID 1 zeros. Equivalent to the wider, okay. It's logically equivalent to a wider RAID 1 0 RAID, but it's generally implemented using software RAID 0 over hardware RAID 10. Oh, okay. That makes sense. So you would buy this. So okay. So you would buy this a RAID piece of hardware that has all of this together, and then you have another one that gets all of this together, and then another one that has all, or whatever, however many more you want to put in. So they come in clusters, which is also handy. Okay. And then really comparison. If you want to get into the weeds, get into the weeds. It's very, very interesting. When I first started at the company I'm working for, tech tip. Not even a tech tip. This is just a good life lesson. Lots of people never learn this. When you're in technology, my computer is extremely important to me, and how I access the computer is also very, very important to me. The most important person in the company to be good with, well, there's a couple people. One, the network administrator, or whoever your point of contact is for your IT department. Whoever that is, be friends with them. You don't have to be like great friends and go out for beers every Friday or anything like that, but you do want to be friendly with them and nice to them. And the reason is, they control who gets the best technology stuff. So, I love the guy who works for our company. He's the best. I've never run into somebody who's better than him. I'm not giving you his name because I don't want him to leave the company because of his reputation. Anytime I've ever had a trouble, I've always gone to him. But one of the things is, when I first started with the company, it was before COVID, we had a luncheon together, and I ended up sitting down next to him. And I had already met him because he provided my computer for me. And so I was asking him about our server and what RAID service it used. And we were able to have a pretty cool conversation about that. But I was honestly interested in how it gets done, because the only experience I had was in schooling like this. And he was able to describe it in ways that I wasn't able to kind of understand completely, but that's okay too. But get good with the IT person. Even if they're not nice, that's okay. Figure it out. At a university, I find that the other person that's really important is the person in charge of printing. Figuring out how to be nice to them is also really good too. But even any of the support staff, you should always try to be as good to those people as possible, because they're working hard too, and we should all be appreciative of each other. Not that you should be mean to anybody. Although sometimes, when your little brother's bothering you, you got to do it. There's nothing you can do about it. I have little brothers too, so I understand. There's a few more things. There's some new future things that we could look at. The book talks about a few of them, but I'm not really too worried about it. There's some really neat stuff out there. Some of which there might be something in the future, right? Because I remember a time when we used these floppy disks for everything, and we had the 5.5s that were actually floppy, and then the 5.25 and the 3.5s, which weren't floppy. They're solid. I don't have any. I don't need them. The computers don't use them. I don't even. If I had one, I couldn't put it into any of my computers because I don't have a drive for it. It's also true for CDs or DVDs. I don't have any. No, not true. My old laptop that I had in grad school, which I still have, does have a DVD reader. So if I had to, now I couldn't do a Blu-ray, but I could do a DVD. So fair enough. Anyways, there's some new ones. At one time, CDs weren't a thing. They didn't exist. They had to come up with them. They had to develop them. And so it's the same thing, right? The same thing with those floppy drives. They didn't have them, and so somebody came up with them. And so somebody's working on these new technologies, but they're all just potential. So I don't really want to spend too much time on them because eventually they'll become reality and we'll have to figure out how they work. Or we might not have to figure out exactly how they work, but it's a good idea to have some understanding of how it is. So that's it. I love RAID stuff. I think it's really neat how people have figured out how to kind of balance those things out and get some redundancy. Well, we did not end early, but we are not ending late, so I guess there's that. And I will be back. We're going to move on next time and talk about... what's the next one? Software systems. Or system software, operating systems particularly. And I know a fair bit about that because I've taught an operating system class. So I don't know, how did I? Whatever. Anyways, it's another, and then our next topic, and we should be able to kind of burn through that one pretty quickly. But we're getting close. We're getting close to our end of the topics we're going to cover. We will for sure, pretty for sure, it looks like, what do I have? 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9, 10. Maybe 10 more lectures. And right now, as it stands, we're on the 26th. So 10 more would be the week before Thanksgiving. So that means that I will be done lecturing about the main topics for this course at that point. At that point, we will switch. I need to interleave some Maria in there. I'll give you guys a couple Maria programs. And either I'll probably do some stuff with Marie and kind of walk you through a little bit of it, and then I'll assign something for you. And maybe we won't have assignments at that point anymore, so we'll disperse with some of the assignments. We'll figure it out. It's not a big deal. Keep chugging along. Most of you guys are doing great, so keep on keeping on, and we'll see you tomorrow. All right, bye-bye.